So for both classes, we didn't get quite as far in section 1.6 as I wanted to. So I'm going to pick up there, and then we'll go into section 1.7. So what we are looking at here in 1.6 with problem 16 and 17 is we're looking at equations that are in quadratic form. They're not actually quadratics because they don't have second power, but they kind of look like a quadratic in that this first term in this case is 2/3, and then the middle term is half of that. So like normally with a quadratic you'd have x squared and x. Here we have x to the 2/3, and then we have half of that, which is x to the 1/3, but they're not quite the right powers. So this, and then you're going to have a constant term on the end. So this middle term is going to be our guide as to what we want to use as our replacement variable. So we're going to replace x to the 1/3 with u. So u is going to be x to the 1/3. And then we're going to put that in place of all the x's. So if u is 1/3, then a u squared would be x to the 2/3. For instance, here, let me do it a different way. So if I put in x to the 1/3 squared, x to the 1/3 squared would be x to the 2/3. But we defined x to the 1/3 to be u. So I'm going to take that and put a u in there, and then it'll be u squared. Do the same thing here. If I replace the x to the 1/3 with a u, then I get minus 3 u, and I don't need any other power on it because u is x to the 1/3. Let me fix this. This looks a little bad. Okay, so we have u squared minus 3u, and then we're going to have just the minus 4. And you don't have to write this step. I just wanted to show where everything was coming from. All right, so I'm going to get rid of these parentheses. And you can see we just have a quadratic now, u squared minus 3u minus 4. So if we factor that, we get u minus 4 and u plus 1. Which means by the zero product property, u minus 4 has to equal 0, or u plus 1 has to equal 0. In this case, that would make u 4, and over here that would make u negative 1. But remember, we don't want to know what u is, we want to know what x is. So we're going to back substitute, and we're going to put the x to the 1/3 back for the u. So x to the 1/3 equals 4, or x to the 1/3 equals negative 1. So how do you get rid of a 1/3 power? Well, a 1/3 power is like a cube root. So to undo it, we want to take it to the third power. So x to the 1/3 to the third is just x to the first, and then 4 to the third would be 64. So x could be 64 is one of our solutions. And then over here, same thing. I'm going to take this to a third power, and negative 1 to the third power is just negative 1. So your two solutions are 64 and negative 1, and then you could put those back up here and check them. If you wanted to put that in your calculator, you would just put 64, and then whatever your power button is. On a lot of calculators it's a little up symbol, but it might be like an X to a Y button or something like that. And then make sure that you do here that you either do a fraction using your fraction function, or if you're going to put divide, do parentheses 2 divided by 3. And then minus 3 times 64 to the 1/3 minus 4, and you should get 0 if you want to check that. But just make sure when you do the power that you either put parentheses around this if you're going to put division, or put it to the power of a fraction and use that fraction function on your calculator. Okay, so over here we're going to do the same thing. We can see this is not quadratic, but it looks very similar to quadratic. It just has a -2 and a -1 instead of a 2 and a 1. Again, the middle term is going to be your hint as to what you want to use. So we're going to let u be x to the -1. If I do that, then 2u squared would be 2x to the -2, because again I'm letting u be -1 or x to the -1, so this would be like 2 times x to the -1 squared, and the x to the -1 has been replaced with a u. And then minus 7u plus 6 equals 0. We're going to factor that. That'll be 2u. And then over here we have to have a u. And then we have to decide how we could split this up so we can get a 7 in the middle. We could do, let's see, I'll see it right away. A 3 and a 2 would get us 5 or 6, 7, 8. That's not going to work. What about a 3 and a 2 instead? So if this was 3 and this was 2, that would give us a 4 and a 3, so that's what we want. So the outside would be 4 and the inside would be 3, which would give us a 7. Both of these have to be minus so that I can get a plus 6 on the end. So now we know that 2u minus 3 has to equal 0, or u minus 2 has to equal 0. So we're going to back sub in for what the x was. So this means 2x to the -1 minus 3 equals 0, or x to the -1 minus 2 equals 0. Add the 3 to the other side and divide by 2, and you get x to the -1 equals 3/2. And how do you get rid of a -1 power? Well, there's a variety of ways you could do this. One of the things that you can do is you can put the x on the bottom. I think this is probably the easiest. So x to the -1 is like 1 over x. So if 1 over x is 3/2, I can just flip both the fractions, or I could multiply by x. I think I'm going to flip the fractions. If you have just a fraction on one side and a fraction on the other side, it's okay to flip it. So if I flip this over, I get x, and on this side I get 2/3. And I know it looks like I flipped this, but I didn't really flip it. I just moved the x to the bottom so I could get rid of the negative. Here I legitimately just put the numerator where the denominator was and the denominator where the numerator was. So I said if 1 over x is 3/2, then x over 1 is 2/3. But I left off the 1. So x could be 2/3 is one of our options. Or over here you get x to the -1 equals 2. If I put the x on the bottom so I get rid of the negative, that means 1 over x equals 2. If I flip both sides, take the reciprocal of both sides, I get x equals 1/2. And those are your two possibilities. If you didn't want to do that where you flip those, you could take both sides times x. Let me do that right up here. So like on this step, if I wanted to do 1 over x equals 3/2 and you don't like the flipping it, if you just take this times x and this times x, over here you'll get a 1. Over here you'll get 3x over 2. Multiply both sides by 2, you get 2 equals 3x. Divide by 3, and you get 2/3 equals x. Just like we had down here. So if you like that way better, you can use that. I just like this way because it's quicker, and honestly it makes more sense to me. Alright, so then the last two problems that I want to do are, I believe it's 19 and 20. So in 19, these are called mixed exercises. In 19, I need to solve for this x. And so in order to solve for that x, I'm going to want to get anything that doesn't have an x in it onto the other side. So 1 over x would be 3 over z minus 2 over y. And then at this point I can multiply by x. but that's going to end up with x's in 2 spots over here. So I think the better thing to do here, and there's a variety of ways to do this, I'm just going to show you what I think is the best, is I'm going to find a common denominator over here and make this one fraction so that I can flip it. So I'm going to make this 3y over zy minus 2z over zy. So I multiplied 3 over z by y over y, and then I multiplied 2 over y by z over z. That way these have a common denominator, and I have 1 over x equals 3y minus 2z all over zy. And then I can take and flip this like I did up on the other problem. I can take the reciprocal. So 1 over x equals this, then x has to equal the reciprocal. So zy over 3y minus 2z. Then on this problem, I want to get the a alone. And in order to get the a alone, I've got to get rid of this square root, I've got to get rid of this square, and I've got to get rid of the 4. But I've got to get rid of the square root first because it's the a squared is under it. So I'm going to square both sides. So that gives me c squared equals a squared plus 4. Remember, it's not this square that we're trying to get rid of, it's this square root. So the square root and the square cancel each other out. I still have a square on the a. Then I'm going to subtract 4 from both sides. So I have c squared minus 4 equals a squared. And then I have one last step. I want to take the square root of both sides. And that's always positive and negative. So the positive and negative square root of c squared minus 4 equals a. And then typically it's preferable to have the thing that you've solved for alone on the left side. So just flipping those around, the a to the left and the positive negative part to the right, I have a is positive or negative square root of c squared minus 4. So now we're moving on to section 1.7. So section 1.7 is on, the topic is linear, compound, and absolute value inequalities. So the key here is that we're going to be talking about inequalities to finish up chapter 1. There's a lot of, there's a set of steps up here, but I think it's better to show these as the examples and explain as we go along, rather than with the A, B's, and C's. And so we're just going to jump into these. The biggest thing that when you're solving an inequality, if you multiply or divide by a negative, you must switch the inequality around. We'll say the inequality's direction. So that whatever's in the middle, if it's a greater than, you have to switch it to a less than. If it's a less than, you have to switch it to a greater than. Other than that, this is the main thing that makes solving an inequality different from solving an equation. Notice on these they say to graph the solution set and also to write the solution in set builder notation and interval notation. So we've got to make sure we get all those steps in as we do these problems. So on this problem, we are going to first distribute, just like we would if it was an equation. So 3x plus 12 is greater than 5x minus 8. We're going to move things to their respective sides. That we have so we have the variable on one side, the number on the other. So I'm going to subtract 3x from both sides and add 8. So I have 20 is greater than 2x. These 8's canceled, these 3x's canceled. Then if I divide by 2, I'm going to get 10. Now, I did not ever multiply or divide by a negative in this problem, so I never had to switch the sign while I was solving it. So I end up with 10 is greater than x. However, we typically like this variable to be on the other side, And so I'm going to switch this around. I'm not multiplying or dividing by a negative, but I'm switching the sides of these. And I still have to have the open towards the larger one. So right now my opening, my greater than symbol, is telling me 10 is bigger than x. So that would mean x is smaller than 10. So that would be your initial answer. Now let's do all the things that they want. So they want us to graph the solution set. So if we're going to graph the solution set, that means, actually let's do the set builder notation next, because that's pretty easy from what we have. So the set builder notation is just taking what we have here and making it kind of fancy. So we're going to put a set bracket. We're going to tell what our variable is. So the set of x's, because we were solving for x, where x is less than 10. That's all they mean by set builder notation. It just means to take this answer that you had and make it a little fancier form. Okay, so now when we graph this, if we want all the x's that are less than 10, that means that we're going to start at 10 and we want all the numbers that are smaller than that. If you have the x on the left side like it really should be, the arrow will tell you which way to shade. And then because we don't want to include 10, because it just says less than, not less than or equal to, we're going to make a curvy bracket. So a curvy bracket, and then we're going to shade downward starting at 10. And then the interval notation goes really well with the graph. The right side will be the same as what's on the graph, so an open, a curvy bracket at 10. And then here we never stopped, so that means we must have gone to negative infinity. So negative infinity up to 10. Nothing past that. So those are your three things. This is your set builder, this is your graph, and this is your interval. Alright, so let's try another one. So on this one, I'm going to distribute the 8 through. So we have 16 is less than or equal to 8x minus 16 minus 3x plus 5. I'm going to combine like terms on the left. That'll give me 16 is less than or equal to 5x minus 11. If I put the 8x with the negative 3x, and then the negative 16 with the 5. And now I'm going to add 11 to both sides. That'll get me 27 is less than or equal to 5x. And this isn't going to come out as a nice whole number. We end up with 27 over 5 is less than or equal to x, which means x would be greater than or equal to 27. I think I said 27.5. It'd be 27 fifths. So it's not a real, beautiful looking answer. It doesn't come out to be a nice whole number. If you wanted to write it as 5.4, you could do that. Because that's what, if we divide that in, you'd get 5 2/5, which is 5.4. Let's make sure we have all the things. So in set builder notation, we say x, where x is greater than or equal to 27 fifths. That's one thing that we need. Then I like to do the graph next. So my graph, 0 would be here, 27 fifths would be up here. If you wanted to be more detailed, again, it's like 5.4. And then it's greater than or equal to, so I want to make sure I put a hard bracket here and then shade to the right. Let me fix my 27 fifths here so that you can read it a little better. So again, this starts at 27 fifths. And then if I go to my interval notation, it's going to start at 27 fifths, including it, so a hard bracket, and continue to infinity. So those are the three things that we need. Okay. So I have a little bit more room on these two. Thank you. Thank goodness. Okay, so on these two, I think I'm going to go ahead and multiply both sides by 10 to get rid of the 0.3 and the 0.5 having a decimal in them. So if I multiply this side by 10, then I get 3 times x minus 4. But then I have to, of course, multiply this side by 10, which would give me 5 times x minus 6. You could distribute first and then multiply by 10. It really doesn't matter. Next, I'm going to distribute. So I have 3x minus 12 is less than 5x minus 30. I'm going to add 30 and subtract 3x. So that'll give me a 2x on this side if I subtract 3x. Then I'm going to add 30, which will give me an 18. So divide by 2, divide by 2. 9 is less than x. This is supposed to be a 2. And then if I flip that around so that the x is on the left and the 9's on the right, I get x is greater than 9, which would look in set builder notation, set of x's where x is greater than 9. If I graph it, my graph is going to start at 9, and I want everything bigger than that, but not including it, because it doesn't say greater than or equal. And again, if you have your x on the left side, the little arrow shows which way to graph it. Graph it to the right. Okay, and then my interval notation, it's going to start at 9 with a curvy bracket, and it's going to go to infinity. Okay, so on this next one we have not decimals to clear out, but we do have fractions to clear out. So we're going to get rid of the fourth and the third and the half by multiplying everything through by 12. So 1/4 times 12 is 3, so I get 3x. 12 times 2/3 would be 8, because that's 24 divided by 3, which is 8. So this is plus 8 times x plus 3. And then that's greater than or equal to, again, I have to multiply by everything, so take the 12 times the x. That would be 12x. And then 12 times half would be minus 6. And that's just a little nicer to look at, even though it's got a little bigger numbers, it doesn't have those fractions in there. So distribute on this side, I get 3x plus 8x plus 24 is greater than or equal to 12x minus 6. That gives us 11x plus 24 is greater than or equal to 12x minus 6. I'm going to subtract 11x and add 6, and we get that 30 is greater than or equal to x. Put the x on the left side where it belongs, and I get the set of x's where x is less than or equal to 30. Graphing it, I would include 30, but go to the left, so hard bracket at 30, and then shaded left. And then last but not least, our interval notation starts at negative infinity and goes to 30, including 30 just like it did on the graph. So on these next couple, I'm going to solve them, but I'm not going to do the graphing and the interval notation and all of that. Again, just because I'm not doing it on the examples doesn't mean if you came across one on the test, you wouldn't be asked to do that, or if you come across one on the homework where it asks you to do it. But we've done several where you can kind of see how you do that now. So I'm just going to solve these and then go on. So this ends up being 3x minus 9 plus 17 is less than or equal to 2x plus 8 plus x. On the left side, oh, this might be a moot point because these might be special cases. So 3x, and then the 17 minus 9 makes, if I combine the like terms there, that would get me an 8 here. And then that's less than or equal to 3x plus 8 over here. So this is always true. 3x plus 8 is always less than or equal to 3x plus 8 because it's always equal to it. So this is all real numbers. So this is negative infinity to infinity. If you graphed it, you just color in the whole number line, and set notation is, or set builder notation is x, where x is an element of the reals. And again, you'd shade in the whole number line. This one, I believe, comes out with no solution, if I remember right. So if I multiply both sides by, or everything by 8, so I can get rid of the 4 and the 2, that'll give me an 8x on the left. And then that should be greater than 2 times 2x plus 1, because the 8 and the 4 cancel to make a 2 on the top. And then the 8 and the 2 make a cancel to make a 4, so I have plus 4x. So 8x is greater than 4x plus 2 plus 4x. And so we need 8x to be greater than 8x plus 2. Well, that's impossible because the right side here is always going to be 2 bigger. On these, you both have 8x's, and so the 8x plus 2 has to be bigger than the 8x. Another way to look at it is you can subtract 8x from both sides, and it would say 0 is greater than 2. Well, that's a false statement, and so this is going to have no solution. We have a statement that's never going to be able to be made true, so nothing will work for this. Okay, so these next few, you'll notice we have an or and an and in each of the problems. Or means that you take the union of them. It means it's one or the other. So if you're thinking about, like in everyday language, when we say we're going to do something or something else, it means we could do one, we could do the other, or we could do both. So if somebody says, I'm going to go to dinner or a movie, technically they could go to dinner and the movie, and it would still be, they still did one or the other. And is a little bit easier to explain in everyday language. If you think of it as an intersection, then you think about if you're coming down a road and say you have one road is first and the other road is main. If you were going to be at the intersection of first and main, that means you're right here, only where they both cross at. So this is the intersection. The intersection means you're on first and you're on main. Not one or the other, but both of them right in this intersection. You can use actually that street analogy for this too. If you were on, let me just erase the middle here. So if you were on these roads and you told somebody you were going to meet them on first or main, that means you could be anywhere along first or anywhere along main. It's not just the small intersection where they both cross. It would be anywhere along in either of those roads. So an intersection is going to be smaller and a union is going to be bigger. A union is going to include everything, and an intersection is just going to include what they both share. So in this case, we've got 2x is greater than 10, or 2x minus 3 is less than 5. So it can be one or the other, and we would still include it. So if I divide by 2, x is greater than 5 for this first part. Oh, those do not look like 2's. Try that again. And so x is greater than 5, or if I add 3, I get 2x is less than 8. Divide by 2, x is less than 4. So if x is greater than 5 or x is less than 4, we're going to include it. That doesn't leave very much out. So here's 0. here's 4, here's 5. So greater than 5 would start here and go upward. And then less than 4 would start here and go downward. And as long as we're in one or the other space, we're going to count it. So our set builder, or our interval notation, would go from negative infinity up to 4, not included, union 5 up to infinity. And our set builder notation would have the set of x's where x is greater than 5 or less than 4. You could put another x, or you can just, we already know it's x's, so you could put or less than 4. So there's your graph, your interval, and your set builder. You got to have all three of those on most of these problems. Now this has an and in it. That means we're going to find each of them, but then we're only going to graph and use as our solution where they intersect at. So here we have 6x minus 12 is less than or equal to 10. So 6x is less than or equal to 22. So divide by 6. X has to be less than or equal to 11/3, which would be 3 2/3. But also, if we divide by 5 over here, x also has to be less than 2. So we only want where those intersect at. This is kind of a strange problem, and I've thought about actually changing this on the notes, but we'll go with it. So if you start at 11/3, again that's like 3 2/3. So 1, 2, 3, 4. And you say I want to graph less than or equal to 11/3, then that would be from about here downward. But then we're supposed to intersect that with, and let me use a different color because you can see it better, with where x is less than 2. So only where both of these reside can I keep. And in this case, where they both reside is everywhere from 2 down. So the second part is actually the whole solution, the solution to the whole thing in this case. Because the x is less than or 11/3 actually runs over it. So our solution is from negative infinity up to 2. That's where they both are. And we don't need the x is less than or equal to 11/3. We can just do the set of x's where x is less than 2, because that's where they overlapped at. And then I'm not going to do 9. It's very, very similar. They've just got some fractions in there. So now we're going to do the last one where we have an and or an or. We have a 1/2 on this side, so I'm going to multiply this one by 2. And remember, an and is going to be an intersection. So I have x is less than 6x plus 10. I'm going to go ahead and subtract 6x here so we can see this in process. So we have negative 5x is less than 10. So what I want to do is I want to divide by negative 5. But remember, if you multiply or divide by a negative, you're supposed to switch the sign. So x is greater than negative 2. 10 divided by negative 5 is negative 2. Over here, I just need to divide by 6. So I have x is greater than negative 2, and x is greater than or equal to negative 3. So when I go to graph this, I'm going to graph x is greater than negative 2. And then I'm going to graph x is greater than or equal to negative 3. And we're only going to keep where they overlap at. Let me do that in a different color. So where do they overlap? They overlap from -2 up. So from -2 to infinity is where they overlap. And so our set is x, where x is greater than -2, not included. So just at -2 on up is where they overlap. So that's your 3 parts to your solution. Okay, so on the next one, you notice that we have what's called a 3-part compound inequality, meaning that we have 2 inequalities here. First of all, when you have a compound inequality, these inequalities always have to be less than, because that allows the smallest number to be on the left and the biggest number to be on the right, which just kind of makes sense in the way that you're looking at it. And in doing the 3-part inequality, you literally want to think of it like an equation, but instead of just a left and a right, it has a left, a right, and a middle. So if I want to get this x alone, I'm going to add 3, but I have to add it to everything. So I get 2 is less than or equal to 2x, which is less than 5 and 3, which is 8. Then divide everything by 2, and I get 1 is less than or equal to x is less than 4. And that literally means that x is between 1 and 4. So when I graph it, here's 0. I'm going to start at 1 included, and then I'm going to go up to 4, but 4 is not included, and then it's everything between those two. So it's basically the intersection between x is less than 4 and x is greater than or equal to 1. It's where they overlap, which is right there in the middle. Set builder notation would go 1 to 4 like that, or I'm sorry, interval notation. And set builder notation would just be the set of x's where 1 is less than or equal to x is less than 4. So we just put the fancy stuff around this solution. Let's go down and do this one. We'll hold off on that one just for sake of time. So if I subtract 1 from all parts, I get -4 is less than -4y is less than or equal to -2. Now at this point, I have to divide by a -4. But when you divide by a negative, you're supposed to switch all the signs. So this is 1, but this is greater than, y is greater than 1/2. But you notice how now we have the smaller number on the right side. So this should be greater than or equal to. We have the smaller number on the right side, and that's not how we want it. We always want the smaller number on the left. So we're going to flip this whole thing around and say 1/2 is less than or equal to y is less than 1. And so when you graph that, y is literally between 1/2 and 1. So like here's 0, here's 1. If I make this 1/2, we're going to start at 1/2 included, and then that's supposed to be a square bracket. It doesn't look very square. And then we're supposed to go up to 1, not included. So everything between those two numbers is included. So now we have problems where you have an absolute value sign included in your inequality. So we can't forget that that absolute value sign is there. We can't distribute through it because it's not a parentheses. So if we add 1 to both sides, we get 5 times the absolute value of 2x minus 3 is greater than 10. Divide by 5 on both sides, and you get the absolute value of 2x minus 3 is greater than 2 when I divide both sides by 5. So now if you think about what could be inside of this absolute value in order to make it greater than 2, we need in here to either come out as like 2 or 3. Well, not a 2 because that would actually be greater. That would be equal to. But anything just above 2 all the way to infinity. But you could also have anything that was smaller than negative 2. Because, for instance, let's say the inside of here came out to be negative 5. When I take the absolute value of that, I get 5. And 5 is greater than 2. So we're going to split these like we did before, but it's going to be 2x minus 3 is greater than 2, or 2x minus 3 is less than negative 2. So when you take that out, it has to be greater than the actual thing and then less than its opposite. If this wasn't greater than, if it was less than, then you would switch the sign still. So if it was a less than, this would be a greater than. Add 3 to both sides, I get 2x is greater than 5, and so x is greater than 5 halves. Or, if I add 3 to both sides, I get 2x is less than 1, and x is less than 1 half. So when I go to graph this, the x's that will work are anything that's bigger than 5 halves, which is like 2.5. So as long as it's bigger than 5 halves, it'll work, or less than 1 half. So I get these two just disjoint parts of the graph. When I graph that, I have from negative infinity up to 1 half, not included, union 5 halves up to infinity. This one actually doesn't say we have to do all the things, but so this is the set of x's where x is greater than 5 halves or less than 1 half. Connect Math may make you write that x in there again. On this problem, we're going to multiply first by 5 to get rid of the 1/5. So that'll give us 3x plus 3 is greater than or equal to 15. And don't lose our absolute value signs. So if we want to be greater than or equal to 15, then the inside here could come out to be greater than or equal to 15, but it could also be less than or equal to negative 15. Because if I, for instance, say I got a negative 16 in here, absolute value of negative 16 is 16, and that's bigger than or equal to 15. So again, you switch the sign and you switch the right side from positive to negative. So if I subtract 3 from both sides, I have 3x is greater than or equal to 12, and so x is greater than 4, or 3x is less than or equal to negative 18, x is less than or equal to negative 6. So as we did up there, you're going to start at negative 4 and go up, and you're going to start at negative 6 and go down, and you're going to have a disjoint answer like this one, where you have part going down and part going up. On this problem, because we're supposed to be greater than or equal to 0, really this can be anything, because remember, an absolute value is always going to give you 0 or positive. And so this is all reals. Interval notation, it'd be negative infinity to infinity. The graph, you just color it all in. The set builder notation, x, where x is an element of the reals. And again, that's because when I take the absolute value of something, I'm either going to get a 0 or a positive. So everything is bigger than or equal to 0, no matter what I put in there. Whoops. And then on this one, this is kind of the opposite. If I had here, if I'm trying to make an absolute value less than a negative 4, that's impossible. Because absolute value, this side is always going to be a positive, and there's no way you can make a positive less than a negative 4. So this is just impossible, so there's no solution. And this is all reals. So last in 1.7, and actually last in chapter 1, we have a couple problems here where we're going to do applications of inequalities. So this problem reads that the pH of the water in a public swimming pool should be maintained at a safe swimming value of 7.4. Slight variations in the tested value are acceptable, but should differ from the ideal by no more than 0.2. So if x represents the exact pH value tested, write an absolute value that represents a safe interval. So they're saying we don't want to get more than 0.2 away. So in other words, it could go up to 7.6 and it could go down to 7.2, and that would be okay. So x is supposed to be between 7.2 and 7.6. Oh, it says solve the inequality and interpret your answer. We just kind of went to that already. I guess what they meant was we're supposed to do x in the middle. Gosh, I'm not sure here. Let me think a second. Okay, so I had to go look at this because I wasn't even sure what they wanted. I think this is kind of a very forced problem. What they wanted, this was supposed to be our answer for B, but what they wanted here is they wanted that if you take the absolute value of x and you subtract the 7.4, that should be less than or equal to 0.2. The difference between what the pool is and 7.4 should be no more than 0.2 away. So then if I take that out of the absolute value, I'm going to have x minus 7.4 either has to be less than or equal to 0.2 or greater than or equal to negative 2. So it has to be in between 0.2 and negative 0.2. In other words, it can't go more than 2 up or 2 down. And so then if I add 7.4 to both sides, 7.4 plus negative 0.2 is that 7.2 that we had here. And then I add 7.4 and 0.2 over here, and I get the 7.6. So I kind of jumped to that right away, but that's what they technically asked for. And then one cell phone service charges a flat rate of $35 a month plus a penny per text. Another company offers a flat monthly fee of $50 with unlimited texting. How many texts would you need to send for the first company to charge you more per month than the second company? So we want to know when $35 a month plus 1 cent per text is going to be greater than, we'll just say greater than because it says more expensive, not more expensive or as expensive. So we want to know when that is greater than the flat fee of $50. So subtract 35 from both sides, and I get 15. Divide by 0.01, and you get that you would have to have 1,500 texts. Yeah, 15 divided by 0.01 is 1,500. So you'd have to have more than 1,500 texts for that first one to be more expensive. So this one, if you don't send a lot of texts, I mean 1,500 in a month, that's like, it's not unheard of because that would only be on average about 50 a day, which isn't unheard of, but it's probably not common for somebody who's not a teen, or unless you use your phone a lot for work or something like that. So you just would have to know what you're texting, how much texting you do to know which one is going to save you money. The nice thing about this one is you wouldn't have any surprises. It's $50 and it never would change, never would go higher. Even though it could maybe sometimes go lower, it also would never go higher. So anyway, that's it for 1.7. And next we'll do section 3.1, because remember we've already done chapter 2. So we're going to go from 1.7 up to 3.1.